Hello everyone, you are welcome to this session of optimization theory. Today we are going to talk a little bit about optimization theory, some concepts of optimization. Optimization is very important in many different branches, in engineering, in business, in finance, different areas that we need to, like for example, to maximize the reward or revenue or to minimize some cost function. So we are always need to optimize the parameter that achieve the required objective. So we have some criteria. For example, if we have a cost function that we like to minimize, then we can represent this as, for example, x of x, and those x can be like vector, like x1 and x2 up to, for example, xn. Those are the parameters that we are looking for to allocate the optimum values for these parameters in order to minimize this cost function, c of x, or risk function, for example. And also we can also maximize. We are looking for maximize utility function or reward function or whatever. So it can be u of x. Okay, so usually we mean by optimization either minimization or maximization. Minimization of cost function or risk function, okay, or maximization of certain objective or utility or reward. So this is generally the concept or the meaning of when we say that we would like to optimize. What are the optimum parameters which achieve the maximization for certain thing? For example, what is the optimum price that we could allocate for certain like stuff that we are selling in order to get the maximization? Because if you put the cost is or the price very low, then your reward can be decreased, and or revenue. And if you put too much, people they can switch to other alternatives, and also the reward can be reduced. So what is the optimum price? What is the optimum, for example, number of the production? Or so we have actually too many problems which could be formulated as optimization problem, minimization, or maximization. We have different criteria to achieve this. So this is what we are going to explain today, the main concepts of these minimization and maximization problem. However, today we will just talk about minimization, because simply the maximization of function ux is the same as minimization of the same function ux, but you add here minus sign. So it will be the same actually. Minimizing the minus sign of the objective function or the reward function, it will be maximization of that reward function. For this reason that today we will talk mainly about the minimization process, and this could be, the results could be generalized here. Okay, first, what we mean by minimization, or what is the point which can achieve the minimum point? This point usually is called the critical or the extreme point. So let us talk about a function with only a single parameter. So we are talking, let's say, about a c cost function of x, and this cost function of x is only in single parameter x. So assume that we have x like x squared plus 2x, for example, plus 1. So this is the cost function, and we are looking for the optimum x which will minimize this function, or what is the critical point of this function. Okay, generally the critical point is that point. For example, if we assume that the cost function is given in this way, this curve is not for this one but just in general. Okay, and now you can see that if we are looking for the minimum point, then the minimum point for sure that it will be this point. This point x star here will be the minimum. Okay, and the minimum function, if we assume that it will go to infinity in both sides. Okay, it goes to infinity in both sides. So we have only a single optimum point here to achieve the minimum point, which is given as x star. Okay, in x, and this is c of x. Okay, what is the properties of this x star? Actually, x star, it has certain and very important property here, is which is the slope at this point. what we mean by slope, the slope at any point, for example, if you assume at x1 here, what is the slope here? The slope here actually is given by the differentiation of this function at x1. So dc of x, dc of x divided by dx, so the differentiation of c of x at x equal to x1, it gives you the slope at this point x1. Okay, so the slope is actually the rate of a change. dc of x over dx is the rate of a change, and from basic math we know that dc of x divided by dx is the same as the limit when delta goes to 0 of c of x plus delta minus c of x divided by delta. Okay, so and if we talk at x equal to x1, simply you can put here just x1. So simply if you take the point x1 and you add little delta, so you will get x1 plus delta here, for example, and then you subtract this point from this point divided by the difference delta, then this gives you the change, the rate of a change, at this point. So the slope at every point is given by the differentiation of that function with respect to x. Of course, here we assume that the function is differentiable, or it is a smooth function. For example, if we have function like this one, and we want to find the differentiation at this point, it will be critical point, it will be delta, which is not function, but this is different topic. So what we mean here, that we talk now about smooth functions. If it is non-smooth function, then we have different way to deal with it. Okay, so now we have this differentiation. Okay, the differentiation gives you two information. First, the rate of a change. Second, the direction of a change. For example, now if when you take this differentiation at this point, for sure it will be negative, which means that the direction of the slope is going down. Okay, however, if you take the differentiation for the same point but in this direction at x2, so it will give you maybe the same rate if they are symmetric, but the direction of a change will be up, which will be positive. Okay, so remember that this is the rate of a change. So here we have negative rate of a change, and this is the rate of a change, can be very fast, but it goes like slowly, and then this will be the point where we change the direction of the rate of a change from negative to positive, and at this point the slope is 0. So the differentiation here is 0. The slope is 0. Okay, so the differentiation at this point, so remember that dc of x over dx at the critical point will be 0. So this is one very important result in optimization theory. This one is very important result in optimization. So the differentiation of the cost function at the minimum point or at the critical point is 0. Okay, so usually we call this point as extreme point, or we can call it as like a critical point. Okay, and actually this will be the same if we talk about the maximum. So if we are talking about the maximum point, so this will be also extreme point or critical point at x star, and again the differentiation at this point will be 0. So when we put the differentiation at any point is equal to 0, it means that we are at extreme point. This extreme point can be minimum and can be maximum. So we don't know yet by looking only to the differentiation itself. We don't know if it is maximum or it is minimum. However, it is possible. It is very easy actually to know that if it is maximum or minimum. One way, if we have this simple case for one parameter, simply you can take, for example, 1 point before it and 1 point after the minimum. So if you find that we go from negative slope to to positive slope, it means that we were at minimum point. If the slope changed from positive to negative, then we were at maximum point, at maximum point. And actually this could be easily found by taking that the rate of the change of the rate of the change. What it means, it means that the second differentiation of c of x. So if we take like d over dx of dc of x over dx at this point, you can see that we take the differentiation of the differentiation. If this was positive, what it means, if it was positive, it means that the change, the rate of a change was from negative to positive, from negative to positive. Then it means that the point was minimum. If the rate of a change of dc of x over dx was less than 0, then it means that the point was maximum. This point was maximum. Okay, so I hope that these basic concepts are very clear. Okay, now we can also talk about 3 different cases where we have the differentiation is 0. So, or 3 different like situations. The first, as we mentioned, when we have negative point. Okay, at this point, dc of x over dx equal to 0, and d square of c, sorry, of x over dx square, if this point greater than 0. The second case, for the maximum point, so in this point, this is at of course x equal to x star, and this is also at x equal to x star. So this is x star here, so we have x star here as well. So at this point, again, we have dc of x over dx equal to 0 at x equal to x star, and the double differentiation, or the rate of the change of c of x dx square is less than 0. The rate of a change from positive to negative. We have another case, actually. It's called saddle point, or the inflection point, where we might have this situation. Okay, now at this point, actually, x star here. So again, we have d c of x over dx at x equal to x star is equal to 0, but the double differentiation, this d square c of x over dx square here is equal to 0. So now we have 3 situations, as you can see them clearly, that we have the case of the minimum point, and we have the case of the maximum point, and we have the case of the saddle point, or the inflection point, where the double differentiation is equal to 0. This point, actually, we cannot say that it is maximum or minimum, and we can observe this in inflection point when we came from maximum to minimum in this function. So we have such case, or such situation, and this is one of the big problems in deep learning, or in machine learning in general, where we can stuck here, actually, because our algorithms, as we will see later, we adapt them according to the change, the rate of a change. We call the gradient change, so that we can stuck in such point, okay, in this inflection point, which is not maximum or minimum point. However, it is still a critical point. Okay, now let us go to another definition. Is that usually for the single function, okay, for the single function, we might have many critical points. For example, assume that for a single function like c of x, cost function, so we might have such situation. And so on. Okay, so now you can see, actually, in such case, that if we assume that now the function, this is the minimum one, this is we are looking for the minimum cost function. Okay, assume this is the global minimum. Since this is the global minimum, then actually we are interested in this point. However, if we solve this function c of x, if we differentiate c of x over dx equal to 0, the result of this differentiation it will be true for this point, for this point, for this point, and for the minimum, and for this point as well, for this point, for this point, and so on. Every point here, every point here, actually, the differentiation will be zero at each point. Okay. Of course, because we are looking for the minimum point, we can check for those points which are achieving the d square of c of x over dx square should be greater than 0 to guarantee that the point is minimum, because we are looking to minimize this cost function, not maximize. Okay, in that case, it will give us such points. It will be this point, it will be true for this point, and for this point, and for this point. Okay, so now we have how many points in this figure? We have 1, 2, 3, and 4. So we have actually 4 points achieving these two criteria. Okay, in which point that we are mostly interested? Of course, it should be the global minimum. This point is called the global minimum. Okay, global minimum, or of course it will be the best optimum point, because we are looking for optimum points. This one will be the best optimum point in this figure. Okay, now how could we know if we are in the global minimum or in the like local minimum? These points are called local minimum. This is local minimum 1, local minimum 2, and local minimum 3, and here we have the global minimum if we know it. Okay, however, we don't know actually which one is the global minimum and which one is just a local minimum. Okay, so how could we solve this problem? Simply, we can substitute these points, okay, in the original cost function. So we substitute this for cost function, for example, for the point x1 star for the first local minimum, and we substitute for the second one, and for the third one, and for the fourth one, because we have 4 for local minimum. And after that, we can select the minimum of those. Of course, the minimum will be this one. Then we know that we are now achieving the global minimum. This is actually a very simple way to do that. However, unfortunately, this is not possible in most of the cases. Why? Usually, we don't have just one variable. In the optimization problem, we have usually vector of parameters. So usually we have x, which can be x1, x2, up to xn. In some cases, xn can be 100 or several hundred parameters. Okay, so we have many multi-dimensional situation. Assume that in every dimension that we might have like thousands of local minima, thousands, and then thousands here, thousands here, thousands here. So at the total, we might have trillions of possible local minima in some big scale problem. Trillions of possible like local minima. The searching is not possible with maybe in many cases we need even supercomputer, and even in supercomputer it might take years in order to find what is the global minimum in some very difficult problems. For example, if we would like to optimize the proteins, for example, and we have too many chains there, and then we want to distribute the molecules in certain situation to achieve certain objective, and in that case we might have like trillions of possible solutions, and or of local minima. Searching for the optimum one is not that easy. So this is called searching method, that where we solve for all local minimum, and then we search for the optimum one, then this is not a practical solution at all. Even actually in some small scale problems, it can, for example, for your personal computer, it might takes like days in order to find what is the global minimum in that case. So this makes the problem of uh, um, of finding the global minimum out of too many local minima is not that easy problem. It is one of the big challenges in optimization theory in general. Okay. um, from this point we can define actually one interesting property of some objective function is called the convexity. Okay, what is the meaning of convex optimization problem? The convex optimization problem is the problem which has only one global minimum, at least within the range that we are searching that problem. So for example, if we have x, and here we have c of x, and then we have such kind of problems, we call this problem, and we are only interested from 0 to xm, or to x like k, for example. We are looking for this range, and in this range it is clear that we have only single minimum point, and this called convex problem. Convex, sorry, this is okay. Let me, yes, takes time. So it is convex problem, or convex optimization. Actually, convex problems makes the solution much easier, much faster. We have like complete set of a theory to solve convex problems. Okay, of course this doesn't mean that it is very easy to solve. Of course it is very easy if we have a single parameters like this one, but also in case that if we have multi-dimensional problem, it is also possible to solve. And once this is actually the main feature of convex problems, once you reach to the optimum point, then this optimum point is global, and this is for the convex optimization, and this is called the convex problems. Okay. Yes. So now how to generalize the single case for the multidimensional case, but before that, I would like just to mention that for the other side of convex problem is called non-convex problems. Non-convex problems is the problem where it might have many local minimum, or many like critical points, and which means that in many situations it is not possible to find the global minimum. But in case for the non-convex problem, many times we are not looking for the optimum point, but we are looking for the satisfactory point. Okay, so in case of non-convex problem, okay, so instead of looking to the point where the differentiation of x, c of x equal to 0, the critical point, as I said that, and the minimum one, the minimum out of those, usually we are looking for x, optimum x, which makes c of x, okay, which makes c of x is the argument which makes c of x less than or equal to certain like c minimum that we are interested. So as far as we achieve this point, we are satisfied with that solution. So we are not anymore looking for the global minimum. We know that there might be much better solution than this one, but still, because to save time, so sometimes we are satisfied with taking the point which achieves certain objective, and that's it. So we are looking for some satisfactory solution, not to the optimum solution. Okay, and this is especially needed when we are working in real-time application, so we need to take action now. So we have, for example, intelligent machine which should take action based according to some situation. We cannot look just wait and looking for the optimum solution, or the optimum reason for that situation in order to find the optimum solution. So, and this, because this can take like several hours, and we have to take action within even a fraction of a second sometimes. So in that case, we are fast looking for the solution which achieve at least some like threshold that we are looking for. Okay, this is in case of single parameter, but what is the situation in case of many elements? In that case, we are looking for actually the vector of differentiation. Vector of differentiation, we call this as a gradient of c of x, and we put here usually x to show that we take the gradient with respect to x, and this should be 0 at the critical point. At the critical point, this should be 0, and this here 0 will be 0 vector actually. Okay, what does the gradient means? Assume now that we have function c, which is function in x1 and x2 and x3, is not function only in single x, but now we have three-dimensional problem. Okay, so the gradient c, simply it could be described as a vector of the differentiation of c with respect with x1, partial differentiation of c with respect with x2, partial differentiation of c with respect to x3. That's it. It is as simple as this way. So it is, we have vector with three elements, and every element it has the differentiation of c with one of those parameters, and this should be 0. Zero vector means that 0 0 0 in this case. So at this point we achieve the critical point. It can be minimum or it can be maximum, or it can be saddle point, but this will be achieved at the gradient of c of x equal to 0. Okay, what is the okay, let us go to the next now. Okay, now this is the case of multi dimensions. So let me, for example, take simple case that actually we started with this before but we did complete. So if we assume that we have a single function with single parameter, that it is x squared plus 2x plus 1, where is the critical point here? Where do you think? Simply dc over dx equal to 2x plus 2 equal to 0. We put the differentiation equal to 0, and then x equal to minus 2 over 2 is minus 1. So at minus 1, this function will have a critical point. Is it minimum or maximum or saddle point? We don't know yet. Of course, it is simple function, so we can't draw it. But assume that we don't know it, so we can do it easily by taking the second differentiation of c. So this will be, we take this differentiation another time, this will be 2. 2 is greater than 0, which means that this point is minimum point, is the minimum point. Okay, this point is the minimum point. Okay, is it convex or non-convex? It is clearly that it is convex. Why it is clear that it is convex? Because the differentiation, it has only 1 0 point. So it is achieved at only one point. So for sure that it is convex a problem in this case. Of course, all quadratic second order equations are, or polynomials are convex problems. Okay, second order. Yes. So this is simply how to do it. Okay, assume now, just came to my mind now, just we have two functions, so x1 and x2. Okay, and this equal to, let's say, x1 times x2 plus 3x1 square minus 2x2 square. Okay, and plus 5. Now we are looking to the critical points of this function. Again, we take now the gradient of c. The gradient of c of x is simply, we take the differentiation with every element. Yes, so now we have just this function, and in this function now we need to differentiate with respect to x1 and with respect to x2. So the partial differentiation of this c with respect to x1, you can see that it will be x2, because the differentiation with respect is with x1, so it will be x2. With respect to x1, it will be a plus 2 times 3 is 6x1. Okay, and with respect to x1, this will be 0. And with respect to this one, this will be 0 as well. So this is the first differentiation. The second differentiation, partial differentiation with the c of x with respect to x2, it will be x1 plus this will be 0, and it will be minus 4x2. So now, and this should be 0, 0 at the critical point, which means that we have two equations, x2 plus 6x1 is equal to 0, and x1 minus 4x2 is equal to 0. So in this equation we have a critical point when we solve for x1 and x2 in these two functions. Okay, and of course we can check now if it is a minimum or maximum point by checking the second differentiation, but it is a little bit tricky how to find the second differentiation of vectors. Okay, let me repeat now. So we have vector x of x1, x2 up to xn. Okay, now I define the gradient of the function, and now we are looking to the minimum point or the critical point of function c of x vector. Okay, now we define the gradient of this c as vector with a partial differentiation of c of x, but with respect to only single of parameter each time. This is the name, this is the reason that we call it partial differentiation. So it is partially differentiated with x1 and then partially differentiated with x2 until partially differentiated with what? With xn. Yes. So we have vector of n elements, and this should be what? Should be 0 at the critical point. Okay. Now, how to define the second differentiation? The second differentiation is defined by the Hessian matrix. What is the Hessian matrix? The Hessian matrix is a matrix defined in this way. So now we differentiate this once more. So now we differentiate c of x square 2 times with x1 and again with x1. So we differentiate it 2 times. And we differentiate again 2 times c of x, but with respect to what here? With respect to what you think, what you guess? Yes, it is with x1 and with x2. Okay, and we continue. The last element here will be the second differentiation of c of x with respect, what is your guessing? With x1 and until xn. Okay, and what is the second element here? The second differentiation of c of x with respect to x2 and x1. Okay, and here it will be the second differentiation of c of x vector with respect to x2 square, double differentiation with x2, which means that with x2 maybe just to keep it in the same way and not to confuse you, it is correct to say it in this way, but with dx2 with dx2 and so on. And we can continue in this way. The last row in the first column, it will be the second differentiation of c of x with respect to what? What you think? With xn and with x1. And the last element will be the second differentiation of x with respect to xn and xn or xn square. So now we have a matrix, and this matrix is n by n. And you can see, for example, the second differentiation here with respect to x1 and x2, and the second differentiation here is with respect to x2 and x1, and actually they are the same, which means that, and this is valid for all elements here, the Hessian matrix is symmetric matrix. Hessian matrix is symmetric. This is very important property because it means that the eigenvalues of this matrix will be like real numbers, and we will see later the importance of this properties, because actually Hessian matrix determine the convergence rate of our gradient algorithms to find the optimum points. But we will come later to this point. Now I want you just to understand three things. The first thing is, what is the meaning of a critical points, which is can be minimum, can be maximum, can be saddle point. Okay. Second, what is the conditions for every situation? the conditions, all of them, they are sharing that the gradient or the differentiation should be 0. And also for everyone, we can determine what is the situation based on what? Based on the second differentiation or the Hessian. So in case of single element, if the second differentiation is positive, means that the point was a minimum. If it is negative, it means that the point was maximum. And if it was 0, it means that the point was saddle point. And now in multi-dimensional element, the condition becomes like that. The You can see here the gradient must be 0 at the critical point. And what about h? How could we determine or check if that point was minimum or maximum, or in between? Because now we have the cost function is function in many different parameters. Okay, so if it is minimum for every point, then the eigenvalues of h, all eigenvalues will be positive. So if lambda I for h, all of them greater than 0, then we know that every point was like a minimum point. If lambda I for all I is positive, if lambda I for all I is negative, then we know that this critical point was maximum for every partial parameters. Okay, now if we have like difference between them, or if we have zeros in the in the eigenvalue, if we have at least 1 0 eigenvalue, then we know that this at least one of them is a saddle point. And if we have some positive and some negative and some zeros, then actually we will have all of the situation. So the cost function can be saddle point and can be positive. It can be maximum with partially with some elements, and minimum in the same time with other parameters. So if this actually we can check based by checking the eigenvalues of the Hessian matrix, and also the condition number of the Hessian matrix. It will give us some indication about the convergence rate of our iterative algorithms to find the optimum solution. Because this is important to remember, not easy that every time that we can find uh, uh, the single point or the critical point by directly solving the problem. In many situations, we cannot find it directly, so we need always to find some iterative method in order to find the solution. So let us stop here about these definitions. And the third thing, of course, that I wanted you to remember is the concept of what is the gradient, what is the Hessian. So it is important also to remember this one. So those are the main points that I wanted to mention about this first video in the optimization. And now we come in the second one to talk a little bit about the unconstrained optimization and constrained optimization, and also the steep descent algorithms in order to find the optimum solution. Thank you, and see you in the next video.